Today starts our unit on exponential functions. And an exponential function, you may have encountered something like this before in science class when things are growing or decaying by a certain percentage. So there's a lot of real life applications to exponential functions. So so today we'll talk about the basics of exponential functions and how they look on a graph and in a table. So an exponential function is written in the form y equals a times b to the x power. Now your a value, this number in front, that is your starting amount when x is equal to 0. Then we have this b raised to some x power. And the exponent being x, that's how you can tell this is an exponential function. If your variable is in your exponent, it is an exponential function. And this b value, that's the growth or decay factor, or what you're multiplying by y in the table. And we'll look at that in a moment. This b value can also be called the growth or decay rate. Now, sometimes your a value is an invisible 1. So something like 3 to the x power, your b value is 3 because that's what's being raised to the power, but we don't have a visible a value, so it's an invisible 1. Now we have what are called exponential growth functions and exponential decay functions, and their structure is both the same, y equals a times b to the x power, y equals a times b to the x power, where your a value is greater than 0 for both of them. They're both positive. But the difference between growth and decay is that b value. In exponential growth functions, your b value is always greater than 1. And in exponential decay functions, your b value is always greater than 0 but less than 1. So in between 0 and 1. Well, what happens if b is equal to 1? Well, that's not an exponential growth function because 1 to any power is just 1. And a couple things to note is that our b value can never be negative. That would not be an exponential growth or decay function. So our b value will never be negative. Now the a value could be negative, but that is not a growth or decay function. So an example of that would be like y equals negative 2 times 3 to the x. Our a value is negative, so it's not growth or decay. So because a is negative, it's not growth or decay. So what we're going to do is we're going to write exponential functions from a table. And what we need here, we need an a value and a b value. So our a value always occurs when x is 0. So our a value is 2. When x is 0, f of x or y is 2. Now to get the b value, we need to figure out what happens to the y values as my x's go up. So I have x equals 0, 1, 2, 3, 4. What is happening to y? Well, to get from 2 to 12, I multiply by 6. From 12 to 72, I also multiply by 6. So since I'm multiplying the previous y value by 6, that becomes our b value. So then our function becomes y equals a, which is 2, times b, or 6, raised to the x power. Now you want to put either the 6 in parentheses or, like I did up here, put the multiplication symbol between the a and the b. So that way you don't think that this is y equals 26 to the x power. Now, is this a growth or decay function? This is growth because our b value is greater than 1. That makes this an exponential growth function. All right, our second example, our a value is 27 because when x is 0, g of x is 27, so we're going to write down 27 as our a value. So a equals 27. Now what's happening to our y values each time? And you may not see it from the first two, but when I look at 81, then down to 27, then 27 down to 9, and down 9 from 9 to 3, I notice that the y values are being divided by 3. Well, we have to write this as multiplying because our form of the function is y equals a times b to the x. So in order to get writing dividing by 3 as multiplication, we can write it as multiplying by 1/3. So if I were to multiply 81 times 1/3, I get 27. 27 times 1/3 is 9. 9 times 1/3 gives us 3. So our b value is 1/3. So now our equation is y equals 27 times 1/3 raised to the x power. Now this is a decay function because our b value is less than 1. Actually, we'll write it. Our b value is greater than 0 but less than 1. All right, our last example here. We don't have x equals 0 in our table, so we're going to have to extrapolate and say, okay, 1, 0, and figure out what those y values are going to be. Well, if I look at the y values from 25 to 125, and then one from 125 to 625, I recognize that we're multiplying by 5. And if I keep multiplying by 5, I get the next number. Well, now going backwards, what number times 5 will give us 25? Well, that will just be 5. Okay, now what number times 5 will give us 5? Well, that's just going to be 1. So that means our a value is 1 and our b value is 5. And again, you can go and verify in this table. 1 times 5 is 5. 5 times 5 is 25. 25 times 5 is 125. And the pattern keeps going. So y equals a times b to the x power. Now, we don't usually write that invisible 1 there, so you could write this as 5 to the x. And this is growth. Why? Because our b value of 5 is greater than 1. So that makes this an exponential growth function. So now on the next page, we're going to graph exponential growth and decay functions. So when we graph these, we have a base of b, and the general shape is shown below. All of our points will start here, 0, 1, and 1, comma b. And if we look at the graph here, we have a point 0, comma 1, and 1, comma b, and it kind of curves up like this. And notice how it doesn't go below the x-axis. That is because in the general form y equals b to the x, we have an asymptote at the x-axis. Now we had vertical asymptotes before when we talked about rational functions, but for exponential it's going to be horizontal. So we will have a horizontal asymptote. Now, the domain of all exponential functions is negative infinity, comma infinity, and the range is going to be 0, comma infinity because our y values can't go below 0. Now, when we start translating it, yes, we will have stuff below the x-axis, but this is just y equals b to the x power. No a value, no h, no k. And our asymptote is y equals 0. Now, the range and the asymptote, they must align. They must have something in common. These must match. Now, it could be the second value in the range is the same as your asymptote, or it could be the first one. So when we generalize this with a, h, and k, a, h, and k do the same things that they've been doing. A is a reflection over the x-axis, and it also tells us shrink or stretch. Now, when we do have an a value, instead of our y-intercept being at 0, 1, it's going to be at 0, comma a. Right? And our h and k, again, will translate left and right, and up and down. We translate the graph horizontally, h units, that's our left and right, and we translate the graph vertically, k units. Now, when we translate vertically, this also moves the asymptote. So when we graph these, we're going to have a table, and we're going to have 0, 1, and 1, comma b be the first ordered pair. Then we're going to make a third row in the table and multiply all those y values by a. We'll identify and graph the asymptote, and then plot the points from the table, and then translate each point based off of h and k. And then finally, identify domain and range. That will be step 6. So we're going to graph these functions. I want to identify a, b, h, and k. Our a value is 1/4. Our b value is 6 because that's being raised to the power. And our h and k are both 0. Well, that means that our horizontal asymptote will be y equals 0. Now, I don't want to do domain and range until everything's been drawn because that could change things. Besides the domain, well, domain will always be negative infinity, comma infinity. So now our table. We're going to make a table. X, Y. We said 0, comma 1, and 1, comma b. But our b value is 6. Now we're going to take those y values and multiply them by our a value, which is 1/4. 1 times 1/4 is 0.25. 6 times 1/4 is 1.5. So I'm going to now cross off the middle row and plot 0, comma 0.25 and 1, comma 1.5. Our asymptote is at y equals 0, so I'm going to draw a dotted line at y equals 0. We cannot touch that horizontal line, so that means the graph has to start just above it, touch these 2 points, and then curve up quickly. So now our range becomes easier to see. Our smallest y value for our range is going to be 0, and it's going to go up to positive infinity. Notice that our k, our asymptote, and a number in the range are all the same. They all align. Now, with letter B, we have some translations. Our A value is 2. Our B value is 3. Our H value is positive 2, the opposite of what we see. And our K value is negative 2. So this 2 in the exponent means we're going to move or translate it right 2. And this right here that's minus 2 means we're going to go down 2. So this means our asymptote is at y equals negative 2. All right, so let's make our table. We have x, y, 0, 1, and 1 comma b, which is 3. Now we're going to multiply everything by our a value of 2, so 2y. 1 times 2 is 2. 3 times 2 is 6. Cross that out. Now drawing our asymptote at y equals negative 2. So that is our asymptote. Now I'm going to plot the points 0, 2 and 1, 6. 1, 2, 3, 4, 5, 6. Now I'm going to take those points and look back at my translation and move each of these points right 2 and down 2. So here 1, 2, and down 2. 1, 2, and down 2. So my graph will now look like this. The domain is still negative infinity, infinity, and our range is going to be negative 2, infinity, because we shifted everything down 2. And again, our k value, y, and range all align. So then on the next page, we're going to talk about how to graph exponential decay functions. So for exponential decay functions, remember a is still going to be greater than 1, but the b value is going to be between 0 and 1. And then, as we said earlier, your b is called the decay factor when you have an exponential decay function. So when we graph these, we're going to graph them the exact same way that we did the growth functions. It's just going to look different. We're still going to use the exact same points, except now we're going to have our b value be a fraction or decimal. So the domain is still negative infinity, infinity, and the range is still going to be 0, infinity unless we have a translation, and the asymptote is still going to be y equals 0. And again, when we have these functions, these must match. The asymptote and one coordinate of the range. So if we look at this example, same thing that we were just doing. We're going to have our a value is negative 2. Our b value is 4 fifths. We do not have an h and k, so 0 and 0, which means our asymptote is y equals 0. So then let's make our table. X, y, 0, 1, and then 1, b, which is 4 fifths. Now we're going to multiply everything by our a value, which is negative 2. 1 times negative 2 is negative 2. 4 fifths times negative 2 is negative 1.6. So now I'm going to go ahead and plot my asymptote and my points. So asymptote y equals 0 and our point, when we cross off the middle, our points are going to be 0, comma, negative 2, and 1, comma, negative 1.6, which is kind of close to negative 1.5. So now our graph has to get closer to the asymptote this way, and that means this way it's got to come down. Our domain is still negative infinity, comma, infinity. Our range, though, because we had a reflection, our range is going to be negative infinity, comma, 0, because we always put the smaller one first. Now again, look at your k value, our asymptote, and one of the coordinates of the range. They're all the same. They all are 0. And if we have a negative a value, our range has negative infinity in it. So those are some things you should watch out for. Now our last example, we have 3 times 2/3 raised to the x plus 1 power minus 3. Now this x plus 1 in the exponent again means we're going to go left 1, and the minus 3 means we're going to go down 3. So let's label our a, h, and k and our b values. So our a was 3, b was 2/3, h was negative 1, the opposite of what you see, and k is negative 3. Asymptote is going to be y equals negative 3. So we're going to make our table xy 0, comma 1, and then 1, comma b 2/3. And now we're going to multiply everything by our a value, 3y. 1 times 3 is 3. 2/3 times 3 is going to give you 2. So our asymptote's at negative 3, so 1, 2, 3. And we have our point 0, comma 3, which is going to be just off the graph, and 1, comma 2. Now we're going to take each of those points, though, and move them left 1 and down 3. So left 1 from the top point, left 1 and down 3. 1, 2, 3. I'm on the x-axis. My other point, left 1 and down 3. 1, 2, 3. So you see the graph is going to go this way now. So our domain is going to be negative infinity, comma infinity, like it's always been. Our range is going to be negative 3, comma positive infinity, because our graph is going up when we look at the left side to all those positive y values. And we can see all of these align, so we know that everything should make sense. All right, so that's it for graphing exponential functions. Again, you just want to follow these steps that we have here to kind of see how you do it if you forget. So thanks for watching. Make sure to like and subscribe.